all around us. The core components of technological products, from smartphones to electric cars, are born in flames of more than 1600 C. The material that guards them is a material that seems to defy common sense, a ceramic with countless micropores. What guards them is a material that seems to defy common sense, a ceramic with countless micropores. Today, let's take a closer look at the hero of the high-temperature industry, recrystallized silicon carbide. Its manufacturing process is a materialistic rebellion. While other ceramics are sintered by adding a binder, it is the ultimate in purity. It is only forged in a sanctuary at temperatures exceeding 2200 C. The silicon carbide particles are then crystallized in the microcosm. Here, the atoms on the surface of the silicon carbide particles sublimate directly into gases that migrate through the microcosm as if they were alive, eventually finding companions and crystallizing again. They hold hands and form an extremely strong skeleton. Throughout the process, no impurities are added. What you end up with is silicon carbide that is 99% pure, but at Opris it is born with 15% to 20% connected air holes. How can porous material withstand extreme environments? That's where its wisdom comes in. First, unrivaled high-temperature stability. Because there is no low melting point binder, when ordinary materials have long been softened, its crystal skeleton is still rock solid above 1650. It is the king of high-temperature creep resistance. Second, top-notch resistance to thermal shock. It can be pulled out directly from the furnace at high temperature without blowing up. Its high thermal conductivity and low thermal expansion make it indifferent to drastic temperature changes. Third, the ultimate purity. It breathes at high temperatures without contaminating the products it carries. This is crucial for the super clean room where chips and batteries are made. In what unseen places does this king of contradictions watch over us? It is behind every lithium battery enhancement. The kiln made of it provides a stable high-temperature environment and absolute purity guarantee when sintering key materials. It is also indispensable for the efficient conversion of each PV wafer. It ensures that the silicon wafer is not deformed or contaminated during high-temperature treatment. In the semiconductor core hinterland, it is more indispensable guardian, carrying valuable wafers through thousands of degrees of process links. It's never directly in the final product, but it's the heart of the manufacturing core. Of course, it has flaws. Its porous structure makes it unsealed, and its room temperature strength is not the highest, and the cost of forging it over 2200 means high costs. But that's precisely lie the wisdom of engineering, trading acceptable shortcomings for irreplaceable longcomings. On the ultra-high temperature, high purity track, it has no rivals. The role of this behind the scenes hero is becoming more and more critical as demand for clean energy and semiconductors explodes. So the next time you pick up a cell phone or drive an electric car, you may want to remember that there is a piece of ceramic full of breathing holes that has guarded their berth in the flames.